Good evening all. As part of APGENCO 2025 electrical engineering paper, we are discussing on electrical networks topic. In that, our today's discussion topic on regarding network theorems. These four theorems are covered in this session. Firstly, starting with the superposition theorem. These theorems are helpful in solving the problems, solving the circuit easily. If this superposition theorem helps in solving the circuit when there is a multiple sources. When there are multiple independent sources, then considering one element, the voltage or current value will be the algebraic sum of contributions from each independent source acting alone. First of all, when we are discussing this theorem, this theorem will be applied in a linear bilateral network. What is a linear network? Linear network means the circuit which contains resistor, capacitor, inductor. Only these three things, then it is a linear circuit. Linear circuit or network should satisfy additive property and homogeneous property. Additive property means if input is applied, then there exists one output, and if another input is applied, then there will be a Y2 output. If you add the both inputs and send to our system which containing the resistor RLC circuit, then the output should also be the additive property. It should exhibit the additive response, homogeneity. If a scalar is added to the input and sent to the system, then the output should be a scalar multiple of that output. And as we can see, resistor, inductor, capacitor are linear elements because V is equal to IR, as R is the scalar, it's a linear proportional, and derivatives, why this derivative can be considered as a linear, because if we want to confirm whether any equation is a linear equation, then it should satisfy this condition. If scalar is multiplied to any function, then it should be an individual multiple of that functions. Derivative follows this same. It satisfies the same. So then derivative operator is also linear. So RLC elements are linear elements. Bilateral network. Bilateral network means the flowing in both the directions, in positive and in negative directions also. So resistor is called as bilateral network, but diode is not a bilateral element. Well, now solving the problem using a few steps. Step 1. Turning off independent sources except one source at a time, and solving the circuit, and at last do the algebraic sum of all contributions to the independent sources. This can be explained in a small example. There are three sources, so first source should be taken and remaining should be removed. If there is a current source, then it should be open circuited. If a voltage source is there, then it should be short circuited. As we are considering voltage source, so the current source are open circuited. So in this question, we need to find V0 voltage by using superposition theorem. So as these are open circuited, current will not flow through this. So only loop we have is this loop. So if you apply voltage division, then the voltage across V0 will be 2 volts. Now considering circuit with 2 amp resistor, the current direction is downwards. So we will divide the current and we apply V0. We will find V0 across as this. here 2 amp is flowing here. There is an equal resistance are there. So the current will be, we can apply current division rule and find the current flowing this one. And multiplying, then we got 1 milliamp on each branch. So 1 milliamp into 1 kilo H, then the V0 will be minus 1 volt, because the current direction is from bottom to top. So we took it as minus. Previously the current direction is from the upwards to down. So it is an positively indicated. Now considering 6 milliamps source. So while considering 6 milliamps, other current source is open circuited and the voltage source is short circuited. So the closed loop for this source is here. Only one source acting one resistor in series. So this V0, the current flow will be 0. So the voltage drop across this resistor also 0. So by doing algebraic sum of all voltages at voltage 4 volts plus voltage obtained with 2 amps source and voltage obtained with 6 amp source, and if we add up all the both, the output voltage is 1 amp. We going to the next theorem, Thevenins theorem. Thevenins theorem is also applied to a linear network. So any bigger network can be redrawn into a voltage source in series with a resistor. To finding VTH and RTH, we can go through a small example. Here there is an two sources, two independent sources, one dependent source. This source is a dependent source. This I1 is current on this branch. As I forgot to mention here, this is the current through this branch, 5 ohms resistor branch. So what is the VTH and RTH values? To find this, first we need to find the open circuit voltage, that is VTH. Finding an open circuit voltage here, the same voltage as 5 ohms resistor is in parallel with it, and so if what the voltage drop across 5 ohms will be same as at the Thevenin's voltage. So now we can this point as VTH as on the same branch. So this node is considered as VTH. So we can divide the current. Incoming current is 1 ampere. Here I2 current flows. Here I1 current flows. So 1 amp is equal to I1 plus I2. So now we know from nodal analysis the current direction is from top to bottom. So VTH minus 10 by 5 plus I2 current, that is current through 5 ohm resistor, VTH by 5. So from this we obtained VTH 7.5. So in these options only 7.5 VTH is this one. So we can take this as a Thevenin's voltage. To find this, how we got RTH, the method I will explain you. To find the RTH value, this is the circuit. This terminal, in this between this terminal, we need to find the RTH. This can be rewritten with all voltage sources will be short circuited and current sources will be open circuited. Dependent sources will be as it is. So as we can see the reformed thing. So as here the branch is disconnected, so we can the current will not flow in this dependent voltage source. So for RTH there are only two resistors in parallel. So the parallel combination equivalent resistance will be the RTH. To find this, we can use a small test signal, apply a test signal Vt at RTH terminals. That means Vt voltage is applied, a current ITH is flown. The current ITH will be divided to and flow through this 5 ohm resistor and this 5 ohm resistor. So the equivalent resistance will be 2.5. So Vt by It will be R equivalent, that is 2.5. So the answer is 7.5 and 2.5. In this theorem, the whole any linear network can be replaced with a current source in parallel with an equivalent resistance between those terminals. So to go through this example, we can take small example. Now the terminals to be found at A and B, those will be short circuited first at the beginning stage. That current is considered as IN, and Rn, the value Rn is same as RTH value. So if you find now the steps to find the IN, that is short circuit Norton's current, that is short circuit current. As we can see, there is an 20 volts independent source across the 3 amps. So the voltage across this is 20. So the current flowing through is 6.67. As we can be directly saying this. So here there is a current source. If we apply an KVL at A, B, C, D and A in this mesh, so what we will get is minus 20. Minus 20 in the sense here applied voltage is same as to this, as these are parallel. So if you start from here, as there is no element here, so start from D, minus 20. If you going from down, so first sign we saw is minus 20. Minus 6 into 10 minus IN current, as there is a 10 amps is coming and IN current is dividing here, remaining current is 10 minus IN. So minus 6 into 6 is the resistor, 10 minus IN. From this we got IN as 13.34. To find RTH and Rn are same. We will apply where the terminals at A and B, we will apply some test signal, that is Vt, and at last we will find Vt by It, then that is the Rn. So we know that voltage sources will be short circuited here, and the current sources are open circuited. So the remaining elements are these two. So they are in series, because this is in series, but there is a short circuit across 3 ohms. So the current will be flowing, bypassing from this. So the equivalent value will be 6 ohms. Now moving on to the next theorem, maximum power transfer theorem. This theorem states that if load resistance is equal to source resistance, then maximum power transferring will be occurs. This can be understood with solving problem or this derivation. If we go through the derivation, it will be clear. So we will consider a small circuit with Rs as a source resistance, RL is the load resistance in series. So the current flowing equation is Vs by total resistance, Rs plus RL. So for power, VLIL. So as we need power at load resistance, so we took power at load. So what is VL? VL is total voltage into same resistance by sum of resistances from voltage division rule. So that voltage into current, then the power is given as like this. So if we need at RL, whichever the value of RL, then that which value will give the maximum power to RL. That condition we are deriving. So we are derivating with respect to RL is equal to 0. So after solving this equation, we are solving this by U by V method, that is U dash, that is the first derivation of U into V minus V derivative of V into U by V square. U is numerator, V is denominator. By applying differential equation, we got Rs is equal to RL. This statement tells When source resistance is equal to load resistance, then maximum power transfer will occur. This can be indicated in a graph that when the RL here if we increase RL from 0 to RL value at the point where RL is equal to RS, then then maximum power will be seen at the load. So while substituting RL is equal to R, then the maximum power transferred will be Vs square by 4RL. So power delivered is equal to power absorbed. So with this, this is a law of conservation of energy. So whatever the power generated, that will be equal to the consumption. So there are two resistors. Each the drop summing of all the powers, then that will be the delivered power. So in placing all the values, Is I have given in the top. If we place the values, then the power absorbed will be Vs square by 2RL. And as we are taking RL is maximum power transfer, so RL is equal to RS. So the power delivered to the circuit is Vs square by 2RL, but the power absorbed by the load resistance is Vs square by 4RL. Then at the load, the efficiency of power absorbed given is 50% of efficiency. So now we considered a resistive circuit, pure resistive circuit. Now we are dealing with impedances which containing resistive element and reactive element. So we are taking the same principle as total Z value is Z as source impedance plus load impedance. After doing this, we get the total impedance. So the current flowing in this Vs by total impedance. So we see similarly we found the power equation. Power is I square R, so I is the same, and into RL. Now first we are considering about RL. In Z there will be two components. One is resistive and one is reactive. So first we will focus on RL, and when we are derivative the power with respect to RL is equal to 0, then what we derived is at load resistance when equal to root of source resistance plus reactances, then at this position we will get maximum power. If the XL reactive drop is varied, then we derivating the same power with respect to XL is equal to 0. Then we confirmed that when XL is equal to XS minus XS, then maximum power will be delivered to the load. So if both are varied, then we are considering the both equations. When XL is equal to minus XS and RL is equal to RS, then it will be a pure resistive element. Then Z will be RL plus RS. So the same value will be repeated here. If load is having only resistive element and the source resistance is having an impedance with a resistive element and a reactive element. So in this condition, we will find the current equation and power equation, then we are derivating with respect to RL. At this position, we are getting RL is equal to under root of source resistance square plus source reactive square. At this point, with this equation, we will get maximum power transfer. So for doing a sample problem on maximum power delivered using maximum power theorem. So let's consider a circuit. We need to find the value of R where the maximum power occurs and also the maximum power delivered to this R. Both we need to find. First, to get the maximum value power delivered, we need to make sure that load resistance should be equal to source resistance. For that, to find at point RL is equal to RS, then we need to first find the RTH value across this point, that will be the source resistance. So to find the equivalent resistance or a source resistance, we need to short circuit the dependent sources. So we are not dependent sources, independent sources. So we are shorting that voltage, independent voltage source. So we redraw this circuit. Our source resistance can be found by applying an test signal. Also, we can find that. So as the active source is shorted, there is no current flowing, so V0 will be 0. So here also the dependent source will be V0 will be 0. If it is a 0, then there is a short circuit across this. So the equivalent circuit will be here, as Vt is applied on this node. Vt is applied throughout this, and Vt will be applied this. So total current is It. We apply nodal analysis here. Then Vt is equal to It by 10 kHz, as it is an V0 is equal to 0. It's a short circuit. So it is, this voltage is not considered. Here another branch Vt by 40k. By solving, Vt by 80 is 8 kHz. 8 kilo ohms. 8 kilo ohms is the RTH value. So by place at 8 kHz is the source resistance. When this source resistance equal to load resistance, maximum power occurs. Now finding the maximum power, we place that 8 kHz in our actual circuit, and we will find the power delivered. How much power delivered at 8 kHz. Here applying at first loop, we will find V0 first, and that V0 we will place in this circuit, and using nodal analysis we will find the current flowing through 8 kHz, and thereafter we will find I square R power. So V0 we found applying in the KCL. It's not KCL, it's a KVL, sorry, voltage here, and applying nodal analysis, and we found voltage as 80 volts. As we know, I square R also we can find, or V square by R also we can find. So V square by R I have used here, and we obtained is 80 ohm by 8K. So the voltage power delivered is 0.8 watts. Now another example, to solve this circuit we will be using one Milliman's theorem. This states that if there are n number of voltage sources in series with impedances, then it can be rewritten as a single voltage source in series with an impedance. So this looks the similar one. In this circuit we need to find the output current. So first what we need to do is, the overall Vm will be V1 admittance. Admittance means reciprocal of impedances. So from this equation we can easily find this I current here. So we are now finding the value, as the voltage source is 200 by 50. 50 is the why we applied admittance, 1 by impedance, 1 by resistance here. And here for this circuit 160 by 40, and as the terminal center are opposite polarity, so we took minus, so is here minus. After solving this, Vm we got is 0. So the voltage, resultant voltage is 0, so the current flowing through this branch will be 0. Reciprocity theorem. This theorem states that if there is a linear circuit, a voltage is applied here and a current is drawn here, if we interchange the same voltage, then the same current will be flowing in the opposite branch. The equation we get is V2I2 is equal to V1I1. These theorems are useful in solving the